we are now going to write all the parameters that allow us to write the link budget for this case, for the radio broadcasting FM radio case we are dealing with. This is just the basic schematics. We have the transmitter, we have the receiver, and the two antennas that are separated 50 kilometers in this case. The power admitted by the transmitting antenna is 1 kilowatt. It's a high power station in this case, but it has a low gain antenna. It's 5 dBs. Those numbers could change in other practical cases depending on the power, depending on the coverage area you want to have, depending on the antenna, where the antenna tower is placed. There are different parameters there. But that's the basic data. Then we have our receiver, which in this case has a low gain antenna. It's a 2 dB, could be even lower depending on how you connect it. And our electronics in the receiver are really here characterized by simple terms. 10,000 Kelvin for the noise, and 10 dBs for the noise figure, and 15 dBs for the gain of the antenna. And now we have to find the received power in terms of the transmitted power. We are going to see those terms written both with numbers and log and decibels. For 1 kilowatt of transmitted power, if you take the 10 log of this value, you will get that this is 30 dB watts. That's the first parameter. And you can really work the link budget directly on the numbers as products and quotients, or as addition and subtraction of decibels. For the transmitting antenna gain, you have 5 dB, so now you have to transform this to linear. You divide by 10, and 10 to 5/10 will give you 3.1, and this is the gain in linear units. The gain is dimensionless, doesn't have any dimension. That's why we use here only 5 dBs. It's just the power ratio. Now we know the gain and the power of the transmitter, so we can combine them, we multiply them, and we get the equivalent isotropically radiated power. And in this case, this system is equivalent to a 3.1 kilowatt isotropic antenna system. But our tower, in this case, is just having some directionality, not much, but it still has some. Now, if you work this on decibels, it's 10 log the power, which is 30 dB watts, plus the gain of the antenna in dBs, 5 dBs. So this gives you 35 dB watts. Then we have to find the free space path loss. And this, remember, is just the ratio of the wavelength to 4 pi r. R is the distance, and a square. The wavelength is just the speed of light divided by the carrier frequency. So you have here 300,000 kilometers per second, and here you have 100 megahertz. You divide them, and this gives you a wavelength of 3 meters. So that's why you can see that your antennas, more or less, may be around half a meter, depending on where you are. That's the basic diameter. I'm sorry, the basic dimension. And 50 kilometers down there. So you just find this, and that's the path loss. This number by itself is telling you that if you put 1 unit in the transmitter, what you will be getting is 2 times 10 to the minus 11 of what you put there. So 1 unit here will be 0 point and then 11 zeros and a digit. That's what you get in this case. So it's a very really heavy penalty for the radio. But the radio works very well, as you will see later. You could write this in decibels. So you just take this number, you get a minus 10, and it gives you 106.4 dBs. I'm putting here a minus sign to tell you that this is a positive number. Losses are positive numbers. But when you account them in the budget, you have to always subtract them. This is like with money. You can gain or lose. And when you write a balance, you know that gains and losses have different signs. So this is exactly the same thing here. So we have this loss of 106.4 dB. Now we can find the power flash density at the receiving antenna, and this is equivalent to the IRP, the equivalent isotropic radiated power, and divided by 4 pi r squared. And this gives you that this is 100.7 nanowatts per square meter. So this is very weak signal from the point of view of power. You can write this also in decibels, and normally, since this is a low signal, we'll use dBMs, milliwatts, as reference. So the first thing you do is you transform this nanowatt number in milliwatts. You have to multiply by 10 to the minus 6. And now you take 10 log of this, and gives you minus 40 dBMs per square meter. And this is just the number for the power flash density at the receiving antenna. Now, to get the received power, we need to do more things. You could follow one diversion here, and it's also find the electric field on the receiving antenna. And the electric field is associated with the power flash density and the wave impedance. You take the square root. So this is telling you that the field is about 6 millivolts per square meter. That means that if you take a length of the field of 1 meter, you could extract up to 6 millivolts, which once again is a low voltage. And you could write this voltage also in dBs microvolt, or this field in dBs microvolt per meter. Now, to find the received power, we need also to know both the receiving antenna gain and the effective area of the receiving antenna. The antenna has a gain of 2 dBs. So now we divide by 10, and 10 to the power of this gives you the gain of the antenna, 1.5. This is a low gain antenna. And the receiving antenna effective area, in this case, the effective area is just the square of the wavelength, which is 3 meters squared divided by 4 pi and the gain. And look at this number, it gives you 1.14 square meter. But remember, the antenna was just a simple wire that you could extend up to about half a meter, a little bit more. But this simple antenna was capturing power as if it had a surface of 1 square meter. Okay? So in this case, the effective area is totally different and much larger. You cannot compare it with the physical dimension of the antenna. And now, since we know this parameter, if we multiply this area by the power flash density, that will give us the received power on the antenna. So we just multiply those two numbers, and we get that the antenna on the receiver will be delivering to that receiver only 100 nanowatts. So your radio works with power levels that are in the order of hundreds of nanowatts in this case. And if you transform the nanowatts to dBMs, you do exactly the same thing. You write milliwatts here, you multiply by 10 to the minus 6, and this is the number you get. Now this is just the signal we are receiving. Now we have to deal with the noise. And the noise, in this case, is associated mainly with the noise that the antenna is capturing from the environment. And we have said that it's approximately 10,000 Kelvin. It could be larger or lower depending on the conditions, depending on where you are. If you are in the urban area, it could be different. Could also be different if there is a storm around you. So those numbers could change, but this is a representative number. You really could use the temperature or transform in dBs. 10,000 is 40 dB kelvins. You also have the noise factor of the receiver, which is 10 dBs, and this means for this noise figure of 10, we also get a noise factor of 10. And the gain of the receiver, which is 15 dBs, which is 31 in the linear scale. And with those numbers now, you can just write the whole thing and find the signal-to-noise ratio at the output of the receiver. We have a cascade of a couple of things here. One is the antenna. There could be also cables in some other cases. Then we have the receiver. So those two blocks, one is the antenna and the other one is the receiver. And here on the antenna, you have the noise that the antenna is capturing from the space. You may have losses in the antenna, so you have to add some noise associated with this. Maybe you have connectors, you have small cables, you have a circuit board. Depending on this, you may also have some losses in there. So those things will keep adding noise. In this case, we have compacted all those terms in just a single antenna temperature of 10,000 kelvins. And we also need to find the equivalent noise temperature of the receiver. Since we know the noise factor, which was 10 minus 1 times the reference temperature and Boltzmann constant and the bandwidth, this will give us the noise added by the receiver. So the power at the output will be the sum of the antenna noise plus the receiver added noise, and we multiply by the gain of the amplifier. And we work those numbers, and we get that the power at the output on this process of the noise is 1.1 picowatt. And if you just transform this into log, it will give you almost minus 90 dBms. We also had previously found the signal, so the signal-to-noise ratio is just the signal level we had at the input of the receiver plus the gain of the receiver. So it was minus 24 dBms, that's the signal level, which is high, much higher than the noise. And if you subtract this from this, will give you the signal-to-noise ratio, which is 65 dBs. That means roughly that your signal level for those numbers is 3 million times the noise level in the receiver. You may think that this is really high and it's really a high number, but be very careful with analog systems because analog systems require high signal-to-noise ratios.